Alright everyone, welcome to my video walkthrough of active learning exercise number 4 for Chem 2101. This is the active learning exercise where you will be using Gauss view to build a molecule. Then you're going to take the molecule built in Gauss view, run it using a computer program called Gaussian, which will optimize its geometry and calculate the IR frequencies. And then you will use that data in order to determine how the IR frequencies will shift when you replace the hydrogens on ammonia borane with deuterium atoms. Now the first thing you're going to want to do is you will want to open up Gauss view. The desktop you have on the computers in the Chemistry Resource Center will likely not look as cluttered as this desktop, but in order to help you find the icon, I will highlight it like so. This is where you want to click right here. So let's double click Gauss view, like so. And you can leave the tip of the day open or you can close it. It really does not matter to me. Actually, this tip here is very relevant to what we're about to do today. So I'll actually leave this up on screen for just 1 second so you can pause the video and read it. All right, let's close it. And the first step is you'll want to build your molecule. All right, the first step is you'll want to build your molecule. Now, by default, Gauss view will start off with a tetrahedral carbon, as you can see here. So to start building your molecule, you simply have to click on this blue window over here, like so. Boom. You've just built a methane molecule. In order to turn this into an ethane molecule, click on any of the protons in the methane molecule and you'll have an ethane molecule like so in its staggered conformation. The next thing you need to do is turn this ethane molecule into an ammonia borane molecule. In order to do that, you'll want to go here and let's turn this to blue so it shows up over here. Click on this button over here and go to N. Now, the default that is selected is nitrogen trivalent, but you do not want to use this because what will happen is if you do, you will lose 2 hydrogens because you want a tetravalent nitrogen atom and not a trivalent nitrogen atom. So in order to prevent this, you want to select this option over here, which just adds a single nitrogen atom. We'll click it and click on one of the carbons in your ethane molecule and you've replaced the carbon with a nitrogen. You'll want to do the exact same thing for the boron. Perfect. Your molecule is now built. The next thing you want to do is go to calculate, which is right up here. Gaussian calculation setup. This window will walk you through what you need in order to set up your Gaussian calculation. You want to select this option, opt plus frequency. What the opt means is Gaussian will take this geometry that you have input and it will optimize it by calculating its energy and then trying to move the atoms a tiny little bit and see if that lowers the energy. If it does, that structure will be the one that is used for the next cycle. If not, it'll go back to the initial and try something else. Now, what it's going to do is it'll keep doing this optimization until it finally reaches a point where it's falling into an energy minimum. At that point, it'll say, I found the lowest energy I can with the starting geometry you gave me, and then it will give you your results. Everything on this page over here is all right. So your next tab you want to click on is method over here. Now this you're going to want to change. You want to go from Hartree-Fock to DFT, and you're going to want to use the PBE method. The method is the set of mathematical equations that you're using in order to determine the energy of the various orbitals in your molecule, which in turn will determine the molecule's geometry. The next thing you're going to want to look at is the basis set. The basis set is basically saying how many orbitals do you want to look at when solving this molecule. The default one is 321G, which is basically a minimal basis set. We're going to use this one over here, the CCPVTZ, if I remember correctly. Yes, that's the one we want. And you're going to want to make sure the charge is 0 and the spin is a singlet, which means that you have no unpaired electrons. If you set the wrong spin or the wrong charge, then Gaussian will not run. It'll give you a message saying this combination is impossible. The basis set, FYI, is basically saying how many atomic orbitals do you want to use in this calculation. The more atomic orbitals you use in your calculation, the more accurate your final answer will be. However, it will also mean that your calculation will take longer, which is an important consideration if you're running a large molecule. Just before we hit submit, I'll show you one last thing that these keywords here mean. This means optimization. This means frequency, as you saw on job type. This is the method. This is the basis set. And this is telling Gaussian that it can write the connectivity between the atoms as it desires. This means it's a neutral species, and this means there's a singlet and no unpaired electrons. All right, so now you can go and click submit over here. Yes, we want to save an input file. You can call this whatever the heck you want. I suggest calling it NH3BH3, but doesn't matter. All right, so we can submit the file to Gaussian, and this will take about 5 minutes to run, depending on how fast the computer is. All right. Now, while we're waiting for that to run, I'm going to walk you through the text file a little bit. We can open it with Notepad, and I'll show you what everything means in here. This line up here, okay, I'm going to use a highlighter. This line up here is basically telling you where the check file will be saved. In this case, it's going to be saved on the desktop. This line here is the same as the line that I just showed a moment ago. It's telling Gaussian what it's supposed to do with the molecule you've given it. This just says it needs a title card. Well, it really doesn't. You can ignore the title card and it makes no difference to your calculation. This is your charge and your spin state, singlet, doublet, triplet, or whatever. This over here is your Cartesian coordinates. This is your x, y. It's not very good y, is it? And this is your z coordinates of every atom in the molecule. And this is the atom you have. You could change this, for example, to chlorine if you wanted to inside Notepad, and it would be doable. You don't have to use Gaussian in order to move things around if you would prefer to do it in a text editor, such as Notepad. Now, what this over here means is you have a bond between atoms 1 and 8, in this case between, this is the one between I'm just going to use red here, between this proton over here is number 1, and this boron here, over here, and that has a bond order of 1.0, so it's a single bond. You can run a calculation just fine, even if you delete all this stuff, so it really doesn't matter. Gaussian will fill in the bonds as required. One final thing to note is that if you do delete this and edit the input file yourself, you must make sure that there are at least 3 blank lines underneath the last row of atoms, like 1, 2, 3, and this one has 4, so it's fine. But if you do this to a Gaussian file, then it will not run. I don't know why that's the case, but it just doesn't work. So don't do it. We don't have to save changes to this. So what we're going to do is we're simply going to go and say don't save and just let the calculation finish up. All right. It would appear that our Gaussian job... Okay. All right. It appears that our Gaussian job has finished running. So you want to close the Gaussian window? Well, not quite yet. We're going to take one quick look at this over here, which is there's a quote at the end of every Gaussian run, which in this case is when you having a meeting of the minds, make sure you have the equipment for it. I don't know who said that, but they are kind of fun to look at occasionally. Let's go back and close the Gaussian window. And we want to open the check file, like so. Before we start, I'm going to point out what to do in case you accidentally close Gauss View. Now, the computers in the Resource Center do not associate .chk files with Gauss View by default. So what you're going to want to do is reopen Gauss View on the desktop like so. You go to File, Open, and you're going to want to select under Files of Type, Checkpoint Files or All Files. So let's select this and reopen it. There you go. So now what you want to do is go over to Results, Vibrations, Run Frequency Check. Yes, you do want to run it. And we want to close this for now. You want to go to Edit Isotopologues. And it looks like for some reason we have already got 3 by default in this. But if for some reason you're missing isotopologues, which you probably will be, go to Columns, Mass, and check these boxes. Like so. See? That will add columns. If for some reason these appear grayed out, just click on Mass here again, and you'll be able to edit the columns again. All right, so it looks like we already have our isotopologues added. So once you have your isotopologue 0, 1, 2, and 3 in this atom list editor, you're going to want to edit them. Now, one thing that's important to check is to see which atoms are bonded to what. H's 1, 2, and 3 in this case are bonded to the boron, and 4, 5, and 6 are bonded to the nitrogen. So if I do this, which you can just do that, 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 that. Let's make this a little bigger. That, that. Like so. What this has done here is isotopologue 1 is I've made the H's on boron into deuteriums. If I clicked 3, they would have turned into tritiums. And over here, what I've done is I've turned all the H's on nitrogen into deuteriums. And now for the fully deuterated one, you want to turn all the H's to 2's. Like this. Boom. Boom. Boom, boom, you're done. So now you can go File, Close, and you want to go to New Data for isotopologue 1. And you're going to want to do this for isotopologue 2 and 3 as well. Boom. Perfect. So now you have your IR data for all your isotopologues. The next thing you'll want to do is go to isotopolog 1, which is the non-deuterated one, and you're going to want to click on spectrum. You can go here and go right-click on it, save data. We'll put it on the desktop, and this is NH3BH3. Now, one thing you want to pay attention to is this area down here. You want to set this from 0 initial to 4,000 final and have a step size of 4, which I'm going to change right now. And this has to be consistent between all of your spectra. If this is inconsistent, what will happen is you'll end up with stack plots that don't line up properly. And you'll have a bad time. So let's hit save. And we're going to do this for the next isotopologs, like so. This is, I believe this is NH3BD3, if I remember correctly, right? Yeah, it is. This is NH3 and D3BH3. And the last one is the fully deuterated one. Four. Save. Perfect. So now you have created your isotopologs, and you have all the data and text files you need for your stack plot. There's a little more work you're going to have to do in order to get these into Excel, however. First, we can close this down here. We can minimize. We can leave this up for a second. It's fine. You'll want to open these text files here. This is this one over here, and delete these top rows as follows. And then save them. Control S is a quick shortcut for saving, by the way. Now, the reason why you want to delete these rows that I've highlighted is because if you don't, Excel will not know which columns are which, and it will basically not import the files correctly. So, okay, there you go. And do this one more time. And we're good. From this point, there's a couple of different things you can do. You can right-click on the file and open it with Excel, like so. This will take a minute to load because I have the ChemDraw add-in for Excel. But that tends to not work reliably. So what I would recommend doing is to open a new workbook in Excel. Control N will do that for you. Let's close this one down so that we're not confused by it. Go to Data, Get Data from Text CSV. And we want to click on this NH3BH3. Hit Import. And by default, it should work just fine when you click Load. I'll repeat this process for all the others as well. There you go. So now what you will want to do is delete this column over here. This is the dy/dx column, which is the area under your curve, and you do not need that column for the purposes of this exercise. I also suggest renaming this one to NH3BH3, like so. And you're going to next want to take your NH3BD3 column, take the middle one, copy it, which you can do by holding Control-C on Windows. On a Mac, it is Command-C, I believe. And let's call this one NH3BD3. The column to the right of this, we're going to want to call NH3BD3 plus 1500. And we're going to want to do this in the cell here. we want to enter equals D2 plus 1500. Now what I am telling Excel to do here is to take the value in cell D2 here, add 1500 to it, and dump the sum into cell E2. If we hit enter, that's what it does. To do this operation on all the cells in the workbook that you're interested in, find the little square at the lower right corner of your cell, and when you see this black cross icon, double click it. This will do the operation on all the cells. The next column will be, actually we're going to copy it first and paste it. This is I think ND3 BH3, yes it is that. And this one you're going to want to add 3000 to it. We'll just copy it over. And this is going to be equals F2 plus 3000. Do the same thing here, like so. And this one here, the last one is fully deuterated version. Control C, we're going to go Control V, and we're going to do plus 4500 for this one. Equals H2 plus 4500. And there you go. Now the reason why you want to do this is so that your plot is actually stacked. This way you're adding a different baseline for every one of your plots, so that the plots sit on top of one another properly. If you don't do this, what will end up happening is you'll have your plots will all sit on the same baseline, will essentially be overlaid. But we want to make a stack plot, not an overlay plot. So the next thing you're going to want to do is to make the actual stack plot. Click up here, then hold down Control or Command on a Mac, I believe. And then click this column over here, C, E, G, and I. Then click on Insert, Charts, Scatter with Smooth Lines, like so. And voila! There you go. Now you have your stack plot. One last thing I would recommend to do to make a nice big chart is to move it to its own sheet by doing this. And now you can give it a title, label the axes, blah, 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 as you would do for any other chart. I'm not going to walk you through this because this is a process that I would assume that you're somewhat familiar with by now. So let's save this, go to File, Save As, Desktop, and we're going to call this like that. Perfect. The last thing you will need to do is close down Excel, and you're going to want to go to your workbook over here and go to page 68. Well, I meant the lab manual. Sorry about that. So question 6 here. You want to complete this table here while in the computer lab. All right. So let's go back to Gauss view. I'm going to move Gauss view over here, so let's put it over here so it's not in the way. The molecule we can just, I'm just going to put it over here for now. And let's reopen the vibrations results. We'll put that over here so it's not in your way. Click on these frequencies from bottom to top or from top to bottom. It really doesn't matter. Click on them like so. And click Start Animation. And then you want to look at the description of vibration, which is in this column over here, and see, does this vibration that you're seeing match up with anything that you're looking for in the column? In this case, it looks like, well, we have ourselves an asymmetric NX stretch over here. And it's occurring at this frequency over here, which is 3479.55 wave numbers. So you'll want to go and write, I'm going to use black. 3, 4, 7, 9.55. There you go. So Once you've done that, let me erase this. You want to keep clicking on these vibrations, like so, and looking at your molecule. This is the same one we just saw, so we can ignore it. It's a doubly degenerate band anyway, so they should be at the same frequency. This one over here looks like a symmetric NX stretch, but it doesn't look like that's being asked of us in the table, so this one can be ignored. What does this look like? An asymmetric BX stretch. Well, you would take this value here, 2451, and plop it in your table. I'm not going to write that down for you in the demonstration, but basically you want to do the same here as you did for the example I just showed you. There's a degenerate vibration. This is a symmetric BX stretch. As you can see, it's very symmetrical. So I would recommend writing that in your table at 2394.17. Your values may differ slightly, but that's okay. That's a twisting motion. You don't care about that. Another twisting, bending motion. You don't care about that one. This is what they call the umbrella bend over here. It's kind of what happens to your umbrella if you're walking in Halifax on a windy, rainy day and it flips inside out. It's a 1287 in this particular example, so I would recommend writing that down. And this is the same thing for the boron, 1146.45. These other ones down here, as you can see, they're just whole molecule twisting and bending and etc. This is the BN bond stretch, which is at a fairly low frequency. And suffice to say, you don't care about any of these vibrations for the purpose of this exercise. You can also look at the vibrations by clicking on the spectrum here, start animation, and if you click on the peaks like so, you can actually see which peak on the spectrum each vibration corresponds to, if you would prefer. I'm just going to do this for isotopolog 3 and find the ND stretch, which in this case is at 2562.35. We're going to write that down when using 2. Come on, right. 62.35. Now, the last thing you're going to want to do in this exercise is fill out this ratio of vibrations column over here on the right. And to do that, you're going to want to open your calculator, which I'm going to do on screen so you folks can see what I'm doing. We'll do 2562.35 over 3479.55. And I got a ratio here of 0.736. Okay. So, once you've got to this point, you're almost done with the active learning exercise number 4 components in the lab. The final thing that you need to do, you absolutely have to do this before you go, is save your data on a flash drive. The USB port to plug in your USB drive should be down here in the lower left corner, at least on this generation of computers. If the computers have been upgraded since this video has been filmed, it may be in a different spot, but that's where it is. So what you want to do now is take your files, hold down Control to select them, Control, click, and hit Control C. This will copy them. And then you're going to want to go to your flash drive, which in this case is over here. Create a folder for your thing. I'm going to call it after my net ID, TR217804. And then I'm going to go paste the stuff in. You should have a total of 1, 2, 3, 4, 5, 6, 7, 8 files. If for some reason you didn't manage to finish every part of this active learning exercise in the allotted time, that's okay. If you have your files saved on your flash drive or on OneDrive, depending on what you prefer or Dropbox or anything, you can always come back to the computer lab, copy the files from your flash drive or wherever they're saved onto the desktop, and reopen them with Gauss View and pick up right where you left off. So anyways, that's everything I have to say for how to complete active learning exercise number 4. I hope you found this walkthrough helpful. If you have any more questions that I didn't address, please feel free to ask the TAs or Mark in the computer lab or the resource center, and we will be more than willing to help you. Goodbye.